Great. In today's video, we're going to be talking about a policeman who detects anomalies in DNA, how DNA goes about making proteins, and some point shift mutations or anomalies that may or may not affect what a protein's function is. We are given 2 strands of DNA, and the policeman's first job is to track down a suspect with 4 total amino acids. Looking back on his police training using a stoplight, he knows that there is one specific start codon, AUG, and 3 stop codons, UGA, UAA, UAG. The policeman deduces that the DNA strand must start with ATG, as the T will turn into a U in transcription with mRNA, and it can start with either strand and go in any direction. The first suspect he finds starts here with the ATG in DNA. That would be the AUG start codon in mRNA, but as he continues studying the suspect, he realizes that the stop codon is not within 4 codons to become amino acids, but rather 5, so this is not the guy. Looking at the bottom strand going left to right, he notices another ATG that codes for a start codon in mRNA, but like the first subject, does not have a stop codon within 4 amino acids and is not the culprit. He then looks right to left on the first strand and finds no start codon, so he moves to the bottom strand. Here he finds the correct culprit with 4 amino acids beginning here and ending right here. The policeman then deduces that the bottom strand is the coding strand and the top strand is the template strand, because the template strand will be used in transcription to make an mRNA sequence that resembles the coding strand, just with the T's and U's switched. The policeman pulled out his handy coding dictionary to then code the mRNA sequence to find its translation into amino acids, in which the AUG is methionine, GUC valine, AGC serine, AAG lysine, and the UAA is one of 3 possible codons. Stop codons. The police station decided to give the policeman a harder challenge to detect the anomalies with the following suspects. In the first suspect, he compared it to the standard wild-type DNA coding strand and found that the original G had mutated to an A. He pulled out his handy cheat sheet and noticed that since G and A are both purines, this is a transition point mutation, and the effect is a missense, because those 3 bases that contain the mutation now code for isoleucine, a different amino acid than the original wild-type valine. The second suspect has switched the C for a G, and this is a transversion point mutation, as the pyrimidine has switched to a purine. The overall effect of this second suspect was a silent mutation because it coded for the same amino acid valine. In suspect 3, an A has been changed to a T, in which the mRNA strand creates an early stop codon and a nonsense mutation that is also a transverse mutation, with the purine switching to a pyrimidine. Finally, the last suspect had switched the last A in the DNA strand for a T, which creates a read-through mutation in the mRNA sequence because it now codes for a different amino acid tyrosine than rather than a stop codon, and the chain continues. This is a transversion mutation, as the purine A was swapped with the pyrimidine T. Here are my references.